Our speaker today is Niklas Hellmer, who will be talking about topology-driven goodness of fit tests in arbitrary dimensions. Take it away.
Well, thanks for the kind introduction, and thanks for having me, and thanks for organizing this amazing series of seminars. I'm going to present joint work with Pavel Drodko, who is my supervisor, Rafał, who is a postdoc in our group, and I think also in the audience. And Łukasz Sretna is a probability theorist at our institute, which is the Institute of Mathematics at the Polish Academy of Sciences. I'm currently actually just outside of Munich, visiting Bastian's group at Hellmer. And this research supported through the Dioscuri program jointly run by the Max Planck Society and the Polish National Science Center. So let me start with the problem statement, namely, what is a goodness of fit test? Because this is going to be mostly a statistics talk given to perhaps not a statistics audience. So if you have some point sample, you might wonder whether it follows a certain distribution. So in this case, I have sampled 100 points on the line, in the unit interval more specifically. So you might think that it might come from a uniform distribution. So you would formulate this as the null hypothesis. The sample is coming from the uniform distribution, and the uniform distribution in this case is called then the null distribution. And there are classical ways to tackle this question. Perhaps the most prominent is the Kolmogorov-Smirnov test. It goes as follows. It looks at what in probability theory is called the cumulative distribution function. So the cumulative distribution function of a sample is you just swipe through your sample from left to the right, and you count like what amount of sample points are to the right. So I don't know, to the right of 0.4 here you have, I don't know, that amount of sample points. Okay. And you can compare this with what you would expect under the null hypothesis. So that is the cumulative distribution function of our null distribution, which is the uniform distribution. This is just the diagonal line, right? This is coming from a uniform distribution. You would expect like half of the points to be to the left of one half, and so on. And how do we compare those two cumulative distribution functions? We take the supremum distance. Okay. And it turns out then that this works well in a specific sense. So if this supremum distance is big, you say you have evidence to reject the null hypothesis. And if this supremum distance is small, you don't have evidence to reject this hypothesis. So the supremum distance is what we call the test statistic. And what I mean by if this is big or small, this is precisely known in the case of Kolmogorov-Smirnov tests. There are tables which tell you for which values of test distribution you should reject the hypothesis. And moreover, you can give p-values. Now, the thing is that cumulative distribution functions really do use the linear order that you have in one dimension. And so it's not straightforward how to generalize this to higher dimensions. Generalizations exist, but you need to think of a way to phrase cumulative distribution functions, and what you basically have to consider is all permutations of orderings of axes, so on, all permutations, or you can already imagine this is computationally quite expensive. So what I want to do is use topology in higher dimensions to answer this kind of question. And this is not a completely made up problem, because high-dimensional data, high-dimensional samples exist. So here are the locations of homicide cases in Chicago over the course of the last year. And I've fit a Gaussian mixture model with 2 components. I might wonder whether this is a good fit, this model. Or I can ask the 2-sample question. Here I have the locations of homicide and arson cases in Chicago again. I might wonder whether these are following the same distribution. Okay. So these are questions that people care about, right? So these are important questions. So the topological gadget, the topological tool I want to use is the Euler characteristic curve. So maybe to give you some intuition how I think of the Euler characteristic curve here, you have a point sample of just 9 points. Okay. As a topologist, I like to think of 9 points here as having 9 connected components. Okay. But what if, by chance, maybe 2 of the sample points are very close together or even coincide? Do I really want to count them separately? Or do I want to count points that are close to each other as being in one connected component, so to speak? So in this example here, these 2 points at the bottom, they are the closest together. And if we allow ourselves this distance, and if we squint our eyes, then they look like close together. We think of them as being in a single component, and we can draw an edge between these two to visualize this. And then we have only 8 components reflecting our intuition. And that is precisely the number of points minus this one edge. Okay, and if we allow ourselves a bigger distance at which we want to consider points which are close together as living in the same connected component, then we also draw edges in there, here. And now we still have 9 points, but we have 4 edges yielding 5 connected components here. As we proceed with this idea, we form a triangle here. And now we have, of course, 4 connected components, but we have 6 edges. So 9 points minus 6 edges is just 3. So what we do is we fill in the triangle and we add the number of triangles again. Okay. And this is what the Euler characteristic is. So the Euler characteristic of some pleasure complex is just the alternating sum of the number of vertices, edges, triangles, and so on, higher dimensional simplices. And as you increase this threshold parameter, this proximity parameter, you add in more simplices, you get the Euler characteristic as a function of this proximity parameter. And this is the Euler characteristic curve. Okay. Yeah. There a question? Okay. Because if you pay close attention, and I mean, there are probably some people familiar with PDA in the audience, right? What I've explained in the intuition on the left-hand side is basically the Rips complex. And what I show on the right-hand side is the Euler characteristic curve of an alpha complex, or equivalently a Czech complex, right? But without going into the details here, any of those will work for what I will explain in the rest of my talk. So we just have to fix one of these constructions moving forward. For actual computations, if we have low-dimensional samples, of course, the alpha complex is computationally the best. Okay, so when I'm showing you some numerical experiments later on, those will use the alpha complex. So, you know this idea of Czech and alpha complexes, filtered complexes. There's this idea of growing balls, right? People in topological data analysis like to think of unions of growing balls. But in this context, now the animation is not, well, now it's playing, okay. If you look at a fixed radius, you increase your sample size, and this is what statisticians and probability theory cares about, right? If you want some limit theorems, you want to see if the sample size goes to infinity, blah, blah, blah. Okay, now if you increase the sample size and you keep the radius constant, then you densely sample your unit square in this case, okay? So this union of balls will become contractible. This is called the dense regime, right? For, I guess, really obvious reasons. So you need to shrink the radius as you increase the sample size. But on the other hand, you should not shrink your radius too quickly, because then there are almost no intersections of balls. There are almost no edges you draw in. And so everything becomes disconnected, and there is not much interesting topology either. So there is some sweet spot in between, and this is called the thermodynamic regime. And there you shrink your radius as you increase the sample size in such a way that the total volume of the union of balls goes to some finite limit. Or in this case, I'm keeping the total volume fixed in this illustration. So we have n, which is the number of points. Omega d is the volume of a union ball, and r to the d, well, Rn is the sequence of radii. So omega d times r to the d is the volume of a ball of radius r, and we have n of those, okay? And this is, you should think of this as a kind of normalization, right? So the Euler characteristic curve, there's the vertical component, which is, we can easily normalize by just dividing by the number of samples. But turns out that we also need to normalize in the horizontal direction, precisely for this phenomenon that we otherwise would not see a non-zero Euler characteristic in the limit for positive radii. Okay. And why is this interesting topology in this regime? Because there have been theorems, functional limit theorems by Thomas and Obada and Roycroft, Krebs and Polonik, which say that if you normalize the Euler characteristic curve appropriately, so you subtract the mean, and then you divide by square root of the sample size, then this converges in distribution to a centered Gaussian process in some special topology, which basically allows you to wiggle your curves a little bit in horizontal and in a vertical direction. Okay, so if you would fix some radius or a certain volume, if you like to think about it like that, and in the limit you will get some Euler characteristic which is following a normal distribution. But the thing is that all these normal distributions play nicely together and arrange in form of a Gaussian process. And now we're in good shape because Gaussian processes are our classical field in probability theory. And so we can leverage some tools that already exist, right?
Sorry to interrupt you here. I think I missed the notation KR. What does this stand for?
Oh, KR. Oh, sorry. This was any fixed choice. So it can be Vittorius Rips at scale R. It can be a Check at scale R. Or it can be alpha at scale R.
Yeah. Perfect. Thank you.
So we just have to fix this, and then we denote it by K. And thank you for asking. Okay. So I'm going to have to introduce a bit more of statistical terminology here. So I'll sample endpoints in some ambient d-dimensional Euclidean space. Each point should be sampled from some unknown distribution in an identical independent and identically distributed way. Okay, and we have some fixed distribution, the null distribution F, against which we want to test. So a null hypothesis is F equals G, and the alternative is F is not equal to G. And I have to apologize that I'm giving a topology talk, and H0 and H1 are not denoting homology groups. Please forgive me. Then we have to introduce the test statistic. So remember, in the classical case of the Kolmogorov-Smirnov test, this was just a supremum distance between the empirical distribution function and the theoretical distribution functions. And this is now very much analogous to what we have here. We have a supremum distance between the Euler characteristic curve of our sample and the expected Euler characteristic curve we would get under the null distribution, under the null hypothesis. And we have to normalize this by square root of n to leverage this theory from the previous slide about Gaussian processes. Okay. Now, as I said, under the null hypothesis, this test statistic should be small, and under the alternative, this will be large. And we want a threshold for deciding whether to reject this test. And so this threshold C alpha we choose in such a way that we give ourselves some false positive rate, which we might want to tolerate, say 0.05, so 5%. And then the probability of the test statistic being greater than the threshold when the null hypothesis is true should be at the significance level. So if this point sample is actually following the null distribution, only 5% of the time we would want to reject the null hypothesis. Okay. I'll give you an illustration in a bit, but first let me talk about computations, because there is the expected Euler characteristic curve, and there is this critical threshold. So how do we compute these things? Okay, and we just do the naive thing, basically. We just do it empirically. We just ask the computer to simulate this for us. Okay, so given an input point sample and a null distribution against we want to test at a certain significance level, we also have as parameters the number of Monte Carlo iterations, basically. And then the output of our algorithm will be the decision whether to reject the null hypothesis and the p-value. So first of all, we estimate the expected Euler characteristic curve by just averaging from m samples. So we draw samples of the same size as this point cloud we want to test. We do this m times, we compute each time the Euler characteristic curve, and we just estimate the expected Euler characteristic curve by some empirical mean, so we just average it. Then next we have to compute or estimate the critical threshold. And we do even more. We simulate the distribution of the test statistic under the null hypothesis empirically. So what that means is we again take samples from the null distribution and we compute this test statistic, the supremum distance, using our new samples here. And we use the average ECC we computed in the previous step as an estimator for the expected ECC. Okay, now then we basically get a histogram, right, of the distribution of the test statistic. And then we can empirically look at quantiles here, and we can choose this threshold C alpha such that the test statistic in our simulations exceeds this threshold only in alpha, with alpha frequency, right? Okay, and this is kind of a preparation procedure. So, well, if you want, we can fit this, if you want to use some sklearn terminology here. And then the actual testing is where finally our sample comes in. We compute the ECC of the sample. We compute the supremum distance between this ECC and our average ECC. And we can get a p-value by counting how many times in our simulation of the test distribution under the null hypothesis we observed a value exceeding this one that we have just seen. And then we return whether this test statistic we have just computed is less than the critical threshold. So that would mean we accept or do not reject the hypothesis. And we also return the p-value. Okay. Now, maybe this will become clearer in an example. And this is the analogous example to the one I've shown you in the very beginning. So now in 2D. So again, our null hypothesis is that this was sampled from a uniform distribution. And so what I do is I have the average ECC, which is in black here, which are computed as an empirical mean using 1000 iterations here. I compute this threshold C alpha, and you can nicely visualize this as having a band of width C alpha around your expected ECC. So if now some ECC you want to test, or this ECC of the sample you want to test, stays within this gray region, and you don't have evidence to reject this. And under the null hypothesis, this is at significance level 0.05, so only 5% of ECCs coming from a uniform sample ever go outside this shaded gray region. So in this case, the blue ECC, so the blue curve is the Euler characteristic curve of the sample. This stays within the gray region. The supremum distance is achieved here. Yeah, I think the p-value was something like 0.41. So we don't have evidence to reject the null hypothesis here, and indeed this was sampled from a uniform distribution. And now another example. Here is an orange point cloud. You might again wonder whether this is coming from a uniform distribution. And it's actually maybe a bit hard to tell with your bare eye. But if you look at the Euler characteristic curve, you see that this is differing very much from what you would expect from something coming from a uniform distribution. Right? This goes way outside this gray acceptance region. And the supremum distance is so big, in fact, that during the simulation of the null distribution, we never saw such a big test statistic. So we have strong evidence to reject the hypothesis here. Oops, I'm going too fast. So topology enables goodness of fit testing in d dimensions. So the Euler characteristic as a topological invariant, this is agnostic of the dimension. This works in arbitrary dimension, right? And I again want to highlight the analogy to the Kolmogorov-Smirnov test, which used this cumulative distribution function, which you can imagine as, sweeping through your point cloud from the left to the right and counting how many sample points you have to the left of the threshold, basically. So this is just counting, or maybe you have some sub-level filtration, and then you just count. And what we now do here is we look at some Vittoris Rips or alpha or Czech complex. So we look at some filtration corresponding to some proximity parameter. And we not just count, but we count in a topological way, namely we use the Euler characteristic. Okay. So this is nice and this works in this example, but as mathematicians, we like proofs. So I want to give you at least the idea of the proof, but I don't want to dive into the details of the probability theory here. So the test statistic, remember that was the supremum distance. This is a random variable, so it has a certain distribution or a density histogram, right? And this threshold C alpha was chosen in such a way that we say if the test distribution is less than C alpha, then we do not reject. And if this is greater than C alpha, then we reject the test. And under the null hypothesis, if we have a test statistic greater than C alpha, then we make what is called a type 2 error. And we chose C alpha in such a way that this probability, which is in this illustration, this shaded blue area, so the area of this shaded blue region should be alpha. Okay. Then we want to compare this and with the distribution of the test statistic under the alternative hypothesis. So this should be big, right, intuitively, for our test to work. And then we can make another kind of error, which is called the type 2 error. Namely, we can fail to reject the null hypothesis when it is actually false, right? So under H1, the probability of that happening is precisely the area under this orange curve to the left of C alpha, right? So this is the kind of error we want to minimize. So this should go to 0 as we increase the sample size to infinity. Okay, so let's look at an example. So if I have just 50 points in my sample, then these histograms, they overlap quite a bit. And you can perhaps see that there is actually quite a high chance of making such a type 2 error, right? But we want to derive an asymptotic theory. We want to understand what happens as the sample size goes to infinity. So now let me increase the sample size and observe what happens. So here we have 50, now 100 samples, 200 samples, 500, and 1,000. Okay, let me show that once again.
Can I maybe ask a question here? So what do you mean when you say under the assumption of H1? Because wasn't H1 just the assumption that they're not equally distributed? So that leaves still lots of options how they would be distributed, right?
Yes. So of course I made some choice hidden in the background for what I chose. So I think here for H0 I chose the then uniform distribution, and I'm just showing the distribution of the test statistic under the alternative where this point sample was then sampled from, I think, a kind of beta distribution, which is just the kind of thing that I've showed you in the example earlier. Okay, so this is, of course, just an example and an illustration, but it gives you an idea how to prove it eventually, right? So,
and what we want to prove eventually, is this the statement that for every other distribution,
yes,
it will go to...
yes, but, yes, but, and this but comes in a bit. So there is a caveat.
I'll patiently wait.
which I'm going to address. But that's, of course, a brilliant question. Okay, so you see here, as we increase the sample size, this orange histogram runs off to the right, whereas the blue histogram, this stays put on the left. Okay, so in this abstract picture here, there a question? Okay,
maybe someone just forgot to mute themselves. I'll mute them.
So, and this gives you an idea how to prove it, right? So we can show that the expected value of the test statistic under the alternative distribution, this is growing like square root of n, whereas this critical threshold is, if you remember this blue histogram on the left, this didn't move. So this critical threshold is actually constant, basically, that does not increase with n. So the distance between these this expected test distribution in the case of the alternative hypothesis and the threshold is increasing. So this probability of making a type 2 error is just kind of a tail probability. And so by some concentration of measure inequality, we can bound this thing and show that it goes to 0 exponentially as n goes to infinity. And if you're interested in the details, you can read our paper. Okay. And now comes the caveat. Namely, we remember from classical topology, the Euler characteristic is not an injective invariant, right? Two different topological spaces can have the same Euler characteristic. And the same holds true in the statistic setting. Namely, two different distributions can have limiting Euler characteristic curves which follow the same distribution. Okay, so this equal with a D means equal distribution. So these are these Gaussian processes that I've introduced earlier. So these distributions might coincide even if the original distributions from which we sample the points are different. So let's denote this with an equal sign with a chi for the Euler characteristic. And this should not come as a surprise. If you're familiar with TDA, our invariants, they are usually agnostic to translation. So you shift your distribution around, or rotations, or reflections, or all that kind of isometry. So here we have picture of two-dimensional Gaussians, and one is shifted and rotated from the other. So we cannot distinguish those. And more generally, this was recently observed by Vishwanath and co-authors. If your distributions admit densities, you can look at the mass of super-level sets, basically. And if they agree, then also these limiting Euler characteristic curves follow the same distribution. So here we have two probability densities on the interval 0, 3. Okay, F here and G here. And F is a quarter on 0, 1, a quarter on 1, 2, and half on 2, 3. And G is just reordered, so it's a quarter on 0, 1, 1/2 on 1, 2, and a quarter on 2, 3. And here you see an approximation of the limiting expected Euler characteristic curve, and you see that they basically coincide. So we could not distinguish those with our test. And so this is perhaps a caveat. So indeed, for this orange histogram to go off to the right, and for this orange density, for our proof to work, we need to exclude these cases. And if you look at it and think about it for a bit, this mass of super level sets, this is not just unaffected by reorderings, but you could also just move some part, like this this interval where the density is 1/2. You could just move it like all the way somewhere else, some large distance apart. So you tear the support of your density apart, which is something which, as a topologist, feels very painful, and you think you shouldn't be allowed to do that. And now it turns out this does not actually change my invariant at all. And the reason for that is because we're dealing with this thermodynamics limit. Because in the thermodynamics limit, this topology is only a very, very, very local phenomenon. So we only look at basically points and its closest neighbors, right? But all global information of the topology is lost in the limit. And there's also hints that for finite samples, the story is much more intricate. Okay? So for finite samples, you would see some global topological information. But we have no theory for the finite samples. I do what I'm dealt. So now some numerical results. The test power is 1 minus the probability of type 2 error. So the type 2 error was the thing that we just showed that we can minimize, which goes to 0 exponentially. So the probability of not rejecting the null hypothesis when it's actually false. And in different dimensions, we compare it with different tests. So our test, which we dub TopoTest, is shown in black. So higher test power is better, and the black curve stays on top. Okay, and the red curve is the Kolmogorov-Smirnov tests, or its generalizations to higher dimensions, which, as I mentioned, require you to somehow look at all possible permutations of coordinates. So this is computationally quite expensive, and it also performs worse than ours. And maybe it's surprising that already in one dimension where you would not imagine or expect topology to be important, our topology-driven test outperforms this classical method. So Kramer von Mises test is another test which uses the cumulative distribution function. So how did we obtain these numbers, this average power? We just tried a bunch of distributions that are implemented in SciPy. So each of these distributions we took as a null distribution, and then we tested samples from each of this distribution. So all to all, basically. And what you see here is the difference in power. So it's our power minus the Kolmogorov-Smirnov power in 3 dimensions for samples of size 250 at significance level 0.05. And so the blue color means that we are performing better. Red color means that Kolmogorov-Smirnov is performing better. So this is something we would still like to understand why, or what it is exactly. So you see there is a lot of white, a lot of zeros in this plot where our tests perform equally well, but what's the feature that differentiates the two? And this is something we would like to understand. One thing to maybe point out is that we do a much better job than Kolmogorov-Smirnov when distinguishing student t distribution from a normal distribution. Okay, so this is something that is very hard for Kolmogorov-Smirnov, but we have an easier time doing that. And I finally owe you some answers to the questions I raised in the beginning. So was this 2-dimensional Gaussian mixture a good model? And we see here, no, it wasn't. So the test statistic is much bigger than what we would allow ourselves under the for the null hypothesis. This is perhaps not too surprising. Now, I also briefly mentioned the 2-sample test. So what we do here is just a permutation test. So here we just simulate the null distribution using permutations, and we don't have a nice theory yet, maybe. Here we have to maybe pay attention a bit more to appropriately normalizing the things to handle samples of different sizes. But yeah, here you see the example of the location of arson and homicide cases in Chicago. And that's quite a big supremum norm and a supremum distance, quite a big test statistic. In fact, under the simulation of the test of the distribution of the test statistic under the null hypothesis, we've never seen such a big test statistic. So we have strong evidence to reject the hypothesis that location of arson and homicide cases are following the same distribution. But for the locations of homicide and weapons violation, well, these curves are quite close together. The supremum distance is achieved somewhere up here. You can barely see it. So we have no evidence to reject the hypothesis that they are coming from the same distribution here. So to wrap it up, we have introduced a goodness of fit test, which uses topology, specifically Euler characteristic curve, and thus it works in arbitrary dimension and it is computable. We do have a theory, and we do have numerical evidence for its performance, and it outperforms state-of-the-art methods, classical methods. Okay. There are some next steps you can think of, namely, well, maybe let's just first mention something I forgot to put here. You can think of other topological invariants. Persistent topology comes to mind. So this is something we're working on. Also, this highlights the need for fast algorithms to compute the Euler characteristic curve. And we are working also, so currently our implementation is in Python, so we want to have it also in R, and we want to have a backend in C++. Then this notion of Euler equivalence, so remember that there was this caveat, this extra node that we needed to make our proof work. So we would like to understand what exactly, what kind of distributions we can distinguish and what tells them apart. Remember in the beginning, I said that for Kolmogorov-Smirnov test, there are tables telling you when to reject the test or not. We don't have that because our test statistic is very much dependent on the null distribution, whereas Kolmogorov-Smirnov, which is perhaps a bit of a surprise, that test statistic does not depend on the underlying distributions. And so this is notoriously hard. So maybe that last step is further in the future than the others. So to conclude, we'd like to point out that you can do not just statistics in PDA. So of course, this is also something very cool and something that people look at, asking whether a point in a persistence diagram is actually significant. But you can also go the other way around and use TDA to answer statistical questions. So it's not a one-way road, it goes both ways. And with that, I would like to thank you for your kind attention. We have a paper published last month. We have a Python package, which you can just pip install, or you can look at our code at our GitHub. And I'm happy to take any questions now or by email if you like. Thank you.
Thank you very much. That was a great talk. Let's please all unmute ourselves so that we can clap together. Great. And while you're all thinking whether you have a question, I already have one question from the chat. Eric wrote it. Namely, can you combine results from the Euler characteristic transform with your test? The Euler characteristic transform is just a concatenation of a very large number of Euler characteristic curves with directional filtrations. You probably know it, but I'm still reading it out for the other people. Turner and McCurdy in 2014 proved that the Euler characteristic transform is indeed injective, and Curry, Turner, McCurdy proved a finite bound of Euler characteristic curves that you have to consider to still maintain injectivity. Sounds that the Euler characteristic transform can use the full power of your statistics.
That would be amazing, of course. But and it's a good question, right? And I've been thinking about it, and I haven't managed a way to get this to work, because what we are dealing with here are point samples, right? And the Euler characteristic transform requires you to have some, some shape, right? Or maybe a simplicial complex or some semi-algebraic set or whatever. And so the question is, how do we make this play nicely with point samples? So that's the first thing. Then these injectivity results, they are about kind of a local and a global topological kind, whereas our results here are very, very local, and we do not see any global topology at all, right? So I don't know how to bring these two ideas together. I would very much like to do it, but I don't know how. I'm happy to hear anybody's ideas.
Actually, on that, No. So in other sort of areas of mathematics, when you're not dealing with a point estimate, when you're not dealing with like an expected value, typically maybe you try to come up with a way of, let's say, estimating a quantile of a distribution. Let's say you're estimating a specific quantile of a CDF, and then you try to show that with enough estimates, some estimator that you have is maybe a uniform or an epsilon approximation of the quantiles across the entire CDF. And then, okay, now you have your sort of your distribution is sort of approximated, and you can sort of use at least some machinery associated with hypothesis testing. At least I've seen in other contexts. Of course, I have no idea how to expand here.
Yeah. And neither do I. Yeah, I mean, this is the kinds of question which obviously arise with my thinking about that. I should say that I'm not a statistician, so I'm coming to this from a topological perspective very much. Yeah, so it was a learning experience, but I'm curious about like how to take ideas from the statistics side to TDA or vice versa.
Yeah, it sounds like maybe you will get some emails later of people having ideas how to connect these topics or something. Okay, any other questions? You can feel free to just unmute yourself and ask. Okay, well, people are still thinking. I have some questions, namely, could you maybe go to slide, I think it was 7 or so. I think that was a pretty relevant slide with this theorem. Yes.
This one.
Somehow with this slide, I had a bit the hope that you would be able to actually compute the distribution for a given, the expected Euler characteristic curve for a given sample size n. But then when you actually got to this point, you said you sampled it. Is there some hope of computing it, or what's your thoughts about that?
There are several questions in there. So let me try to go through that. So this here is normalized in a way. So here you subtract the expected Euler characteristic curve. Okay.
Yeah.
So this is just a statement about the limit, and this is a Gaussian process. So so some trajectory, some path on parameterized by 0 infinity with expected value 0. Okay, and this has some sophisticated covariance structure which you can find in those papers. So this is first of all making a statement only about the limit. Second of all, it is not making any statement about expectations, right? Because you subtract it and it becomes 0. The expected Euler characteristic curve for finite samples, I think, has never been explicitly computed. I think there is some work by, there was a paper by Herbert Edelsbrunner and other people, I'm afraid I don't remember, about the expected number of simplices in Delaunay triangulations you obtain from some random point samples. So you could leverage those results, but they are only in dimensions 1, 2, 3, and maybe 4. And the expected Euler characteristic curve in the limit has been computed only for uniform distributions in dimensions 1, 2, and 3. And that's due to Omar Bobrovsky. So this is kind of what is known. And but these are the kinds of questions that I'm also working on currently. So I hope to be able to tell you more next time we talk, I guess.
Great. Yeah, and it seems like the sampling is also like a very feasible option. So why not just sample it? It's more like I was curious.
And maybe one more comment on that. So the distribution of the test statistic under the null hypothesis, this is essentially the distribution of a supremum of a Gaussian process. And people in probability theory will know that this is a very hard problem. So I will happily leave that to the expert in probability to figure that out.
Yeah, that makes sense. Okay, great. Then let's see if anyone else has a question. If not, then I'll thank you again here and end the recording.